Hi friends, welcome back on our YouTube channel. In today, Statistical Mechanics, we are going to discuss about Grand Canonical Ensemble. We have already discussed about Canonical and also about Microcanonical Ensemble. So now here we will discuss about Grand Canonical Ensemble. So let's start Grand Canonical Ensemble. Here we will discuss about Grand Canonical Ensemble, Grand Partition function, average number of particles, and also about internal energy, heat capacity, entropy and Helmholtz free energy. So these topics we will discuss in our current lecture. So first of all, Grand Canonical Ensemble. Now, what is Grand Canonical Ensemble? Microcanonical Ensemble is a collection of independent assemblies in which E, V and N remains constant, that is energy, volume and number of particles remains constant, and canonical ensemble is a collection of independent assemblies in which temperature, volume and number of particles remain constant. It means a microcanonical ensemble tends to canonical ensemble if the condition of energy is constant is relaxed. So if we relax the condition that the energy remains constant, then a microcanonical ensemble will be tending to canonical ensemble. Therefore, the energy exchange takes place. Actually, in chemical process, the number n varies, and in various problems such as radioactive decay, it is very difficult to keep the number of particles constant, because in radioactive decay, as the time passes, the number of particles starts to decrease. So, in chemical process, the number n varies, and it is very difficult to keep the number of particles constant. Such an ensemble in which exchange of energy as well as of particle takes place with the heat reservoir is known as Grand Canonical Ensemble. So, Grand Canonical Ensemble is an ensemble in which exchange of energy and also the exchange of number of particles takes place with the heat reservoir. The Grand Canonical Ensemble is a collection of essentially independent assemblies having the same temperature, same volume and a chemical potential mu. So, in Grand Canonical Ensemble, temperature, volume and chemical potential remain constant. Now, this is our ensemble, and this ensemble is actually the collection of assemblies. Which assembly? The assemblies in which temperature remains constant, volume remains constant and also chemical potential remains constant. So, Grand Canonical Ensemble is the collection of assemblies in which temperature, volume and chemical potential of each assembly remain same. And all these assemblies are separated by rigid, permeable and dithermic wall. Thus, Grand Canonical Ensemble corresponds to the situation when we know both the average energy and the average number of particles in assembly. Otherwise, we don't know the state of the system, because here energy exchange takes place and also the number of particle exchange takes place, and hence for Grand Canonical Ensemble we know the average energy and the average number of particles in assembly. The density function in gamma space for Grand Canonical Ensemble is rho, and this rho is the function of P, Q and N. What is P? P is momenta, Q is coordinate and N is number of particles. To find the density rho, we consider the canonical ensemble for a system with particles n, volume v and temperature T. We cannot take exactly here v constant, so we focus our attention on a small subvolume v1 of the system, because here we cannot take exactly v constant or volume constant. Let n1 particles be in volume v1 and n2 particles be in volume v2. Since the total number of particles is n, so n1 plus n2 equal to n, and from here n2 will be n minus n1, and total volume is v1 plus v2, that is v, and from here v2 will be v minus v1. So n2 equal to n minus n1 and v2 equal to v minus v1. Here v is the total volume, whereas n is the total number of particles. Also, we assume that v2 is very much greater than v1 and n2 is very much greater than n1. If h1 and h2 be the Hamiltonian of the system, then the total Hamiltonian of the composite system is given by h equals to h1 plus h2. Here h is the function of p, q and n. Therefore, h1 is the function of p1, q1, n1 and h2 is the function of p2, q2, n2. So, the total Hamiltonian of the composite system is h equal to h1 plus h2. Here h1 is the Hamiltonian of the first system and h2 is the Hamiltonian of the second system. The partition function of the total system is Qn, and this Qn is the function of volume and temperature. So Qn is equal to integration dp dq exponential minus beta h divided by h raised to 3n factorial n. Since h equals to h1 plus h2, so we replace this h by h1 plus h2, and therefore exponential minus beta h1 plus h2 will be exponential minus beta h1 into exponential minus beta h2. So Qn is equal to sigma n1 equals to 0 to n 1 upon h raised to 3 n1 factorial n1 integration dp1 integration dq1 exponential minus beta h1 into 1 upon h raised to 3 n2 factorial n2 integration dp2 integration dq2 exponential minus beta h2. And here h1 is the function of p1 q1 n1 and h2 is the function of p2 q2 n2. We choose the relative probability such that sigma n1 equal to 0 to n integration dp1 dq1 rho equal to 1, and therefore sigma n1 equal to 0 to n integration dp1 dq1 equal to 1 upon rho, because this rho will transfer from here to here and we get this value. Now sigma n1 equal to 0 to n integration dp1 dq1 will be replaced with 1 upon rho. Therefore Qn is equal to 1 upon rho exponential minus beta h1 divided by h raised to 3 n1 factorial n1 into 1 upon h raised to 3 n2 factorial n2 integration dp2 integration dq2 exponential minus beta h2. And from here rho equal to 1 upon qn exponential minus beta h1 divided by h raised to 3 n1 factorial n1 into 1 upon h raised to 3 n2 factorial n2 integration dp2 integration dq2 exponential minus beta h2. So rho will transfer from here to here and qn will be here. So the value of rho will be this one. Since qn2 is equal to 1 upon h raised to 3 n2 factorial n2 integration dp2 integration dq2 exponential minus beta h2. So this will be qn2, and therefore rho is equal to qn2 upon qn, exponential minus beta h1 divided by h raised to 3 n1 factorial n1. Since qn equal to e raised to minus beta a, and therefore qn2 upon qn is equal to e raised to minus beta a, and here a is the function of n2 v2 t divided by exponential beta a, and here a is the function of n v and t. Now if we transfer this exponential minus beta a from here to here, then qn2 upon qn is equal to exponential minus beta a n minus n1 v minus v1 t minus a n v t, because n2 equal to n minus n1 and v2 equal to v minus v1. So if we replace this n2 by n minus n1 and v2 by v minus v1, then qn2 upon qn will be this one. Here a is the Helmholtz free energy, which is the function of number of particles, volume and temperature. Now qn2 upon qn is this one. Now if we expand a n minus n1 v minus v1 t in terms of n v t, then this will be equal to a n v t minus n1 del a upon del n2 minus v1 del a upon del v2. Here a is the function of n2 vt, and here a is the function of n v2 t. If we transfer this a from here to here, then a n minus n1 v minus v1 t minus a n v t is equal to minus n1 del a upon del n2 at n2 equal to n minus v1 del a upon del v2 at v2 equal to v, and we neglect higher order term. Since chemical potential mu equal to del a upon del n2 at n2 equal to n, and pressure P equal to minus del a upon del v2 at v2 equal to v. So this is replaced with mu and this is replaced with minus P. So this negative and this negative will be cancelled out. So a n minus n1 v minus v1 t minus a n v t is equal to minus n1 mu plus v1 p. Since qn2 upon qn is this one, and the value of this bracket is minus n1 mu plus v1 p, therefore qn2 upon qn is equal to exponential minus beta minus n1 mu plus v1 p. And if we open this bracket, then this will be equal to exponential n1 beta mu into exponential minus beta v1 p. Now qn2 upon qn is exponential n beta mu into exponential minus beta v1 p, and z equal to exponential beta mu. And what is this z? This z is actually fugacity. So if we replace exponential beta mu with z, then z raised to n equal to exponential n beta mu. So this will be z raised to n1. So qn2 upon qn is equal to z raised to n1 into exponential minus beta v1 p. Since rho equal to qn2 upon qn exponential minus beta h1 upon h raised to 3 n1 factorial n1, and the value of qn2 upon qn is z raised to n1 exponential minus beta v1 p. So if we replace this with this one, then rho equal to z raised to n1 divided by h raised to 3 n1 factorial n1 exponential minus beta v1 p into exponential minus beta h1, or rho in terms of p q n equal to z raised to n divided by h raised to 3n factorial n exponential minus beta pv exponential minus beta h. In the last term, we considered that the system under consideration to become infinite in size or the value of n lying between 0 and infinitive. For thermodynamic function, we define a Grad partition function R, which is the function of z, v and t, is equal to sigma n equal to 0 to infinitive z raised to n q n vt, and q n vt is actually our partition function in canonical ensemble. So rho is this one, and sigma n equal to 0 to infinitive integration rho dp dq is equal to sigma n equal to 0 to infinitive exponential minus beta h divided by h raised to 3n factorial and dp dq z raised to n exponential minus beta pv. So we integrate on either side of this with p and q, and also we put sigma n equal to 0 to infinitive on either side, and we get this equation. Since sigma n equal to 0 to infinitive exponential minus beta h divided by h raised to 3n factorial and dp dq equal to qn, so sigma n equal to 0 to infinitive integration rho dp dq is equal to sigma n equal to 0 to infinitive z raised to n qn exponential minus beta pv, because this is replaced with q and vt. So the value of this will be this one. Since r equal to sigma n equal to 0 to infinitive z raised to n qn, so this is r, and therefore sigma n equal to 0 to infinitive integration rho dp dq equal to r exponential minus beta pv, and also sigma n1 equal to 0 to infinitive integration dp1 dq1 rho equal to 1. So this will be equal to 1, and hence 1 equal to r exponential minus beta pv. Now if we take logarithmic on either side of this equation, then log 1 equal to log r plus log of exponential minus beta pv, and log of exponential minus beta pv is equal to minus beta pv, and beta equal to 1 upon kt, so this will be minus pv upon kt, and therefore log 1 equal to log r minus pv upon kt, and log 1 equal to 0, so log r minus pv equal to kt equal to 0, or pv upon kt equal to log r, and from here p equal to kt upon v log r, and here r is Grad partition function. By ensemble average, the average number of particles is given by average number of particles, that is ensemble average equal to sigma n equal to 0 to infinitive n z raised to n qn divided by sigma n equal to 0 to infinitive z raised to n qn. And since r equal to sigma n equal to 0 to infinitive z raised to n qn, so this is our r and this is also r, and therefore ensemble average or n bar equal to sigma n equal to 0 to infinitive n r divided by r, because n is also present here, so we put here sigma n equal to 0 to infinitive, or n bar equal to ensemble average of n equal to z del by del z of log r. Now internal energy U equal to minus del by del beta of log r, and log r equal to pv upon kt. So if we replace log r by pv upon kt or beta pv, because beta equal to 1 upon kt, then u equal to minus del by del beta of beta pv. Now we differentiate beta pv with respect to beta, so pv is constant and differential of beta is 1, so u equal to minus pv, so this will be our internal energy. Also, heat capacity Cv equal to del U by del T at V. So, if we differentiate this equation by temperature, then we get heat capacity Cv. And entropy can be determined by integration 0 to T dt Cv upon T. So by obtaining the value of Cv from here, we put its value here and we get entropy. And if we know the value of internal energy and entropy, then the value of Helmholtz free energy can be determined by A equal to U minus Ts. Here we end our session. In today's session, we have discussed about Grad canonical ensemble. Goodbye.